Hello, now this is another short video in the Random Linux Stuff playlist. As we all know, we often use SSH as a way to securely connect to a server. In this video, we will look at the different players like symmetric, asymmetric and hybrid encryption, where the main purpose is to securely communicate with other computers. We'll start with an overview and finish with some real life examples. Let's first look at encryption, for which we use a single key to encrypt as well as decrypt. Imagine a client wants to communicate with a server. Then the client will have a single key with which it will encrypt the data before sending it. And when the server receives the encrypted data, it will decrypt it with the same key. This is referred to as symmetrical encryption because you use a single key, and it is by far the fastest method, mainly because it requires less computational power. There's one little problem, however. How can the client share the session key, as it's called, with the server? I mean, if he sends it just like that, anybody can intercept the key, which would make this key completely useless. In comes asymmetrical encryption, which is a solution that uses public and a private key, or a key pair as it's usually called. Now, to make a long story short, a public and private key are mathematically related. This means that one key is generated with the help of the other. Sometimes the private key is derived from the public key, and sometimes it's the other way around. But that's not really important. The important thing is that both keys are related. This means that anything that is encrypted with the public key can only be decrypted by the system that has the related private key. So even though the key pair is really a pair, you can share the public key with anybody and any system you like. There's one thing you should be sure of, and that is that the private key is never shared, because that will be just as deadly as sending the data in plain text. So to end this very high-level conceptual overview, the client generates a session key to encrypt the data between the client and the server. But before it starts sending data, it first encrypts the session key with the server's public key, and then sends the session key to the server, which will decrypt this session key with its own private key. And now that both systems have the session key, secure transfer can begin. Now, before we go to a practical example, there's one little thing that needs attention, and that is the file that will be created on the client, which is called known hosts. This known host file is stored in the users.ssh directory, and its purpose is to store all the public keys of the service that this user connects to. And there is something special about this, but we'll look at that later. Let's first have a look at an example. Now I'm logged into the client as Rocky, and when I list my login directory I see some scripts and other files, but nothing that relates to SSH. Then I connect to the server with SSH. It tells me that the authenticity cannot be established. This simply means that any system can pretend to be this server. So if we really want to check, we could contact the service administrator and compare the fingerprint of the server's public key. So let's do that. The admin on the server lists the files in the etc SSH directory, and when we list just the host keys, we see 3 private and 3 public keys. So, in other words, 3 key pairs. Now, to check the fingerprint, we run SSH keygen on the key that we have received from this server, and we see that the fingerprint matches. So, it is safe to accept the key on the client. So now we can log in, and obviously we have stored the service key for the next session. Back in our client system, we list our login directory once more and see that there's a directory that has been added. We cd into it and we list the contents of the known host file, which is the only file in there. It shouldn't be a surprise, but there's the public key of our server. In fact, it has collected all 3 public keys from the server. Now, what if the server gets reinstalled, or if it generates new key pairs by reinstalling SSH, or for any other reason? Let's just remove all keys and recreate them. So we run SSH keygen to generate the new key pairs. The capital N option simply says no passphrase, and the type of key is RSA. So we generate a single key pair, not 3. So back on the client we try to connect to the server again, but we fail hopelessly and are warned about a possible man-in-the-middle attack, somebody pretending to be the server that I want to connect to, and I have a different key of that server. To solve this, we simply remove the server's public keys from our known host file. So all 3 keys have been removed. And since these were the only keys, we've got an empty file. Now we connect to the server once more and we get the question that we recognize. This time we simply accept and we're back in business. And when we check our known host file on the client, we see we've only got one single public key of that server. So we're very happy and we're done.